Welcome to Mining of Massive Datasets. I'm Anand Rajaraman, and today's topic is MapReduce. In the last few years, MapReduce has emerged as the leading paradigm for mining really massive datasets. But before we get into MapReduce proper, let's spend a few minutes trying to understand why we need MapReduce in the first place. Let's start with the basics. Now, we're all familiar with the basic computational model of CPU and memory, right? The algorithm runs on the CPU and accesses data that's in memory. Now, we may need to read the data in from disk into memory, but once the data is in memory, it fits in there fully, so you don't need to access disk again, and the algorithm just runs in the data that's on memory. Now, this is a familiar model that we use to implement all kinds of algorithms in machine learning and statistics and pretty much everything else. Right? Now, what happens if the data is so big that it can't all fit in memory at the same time? That's where data mining comes in. And classical data mining algorithms look at the disk in addition to looking at CPU and memory. So the data is on disk. You can only bring in a portion of the data into memory at a time, and you can process it in batches and write back partial results to disk. And this is the realm of classical data mining algorithms. But sometimes even this is not sufficient. Let's look at an example. So think about Google crawling and indexing the web, right? Let's say Google has crawled 10 billion web pages, and let's further say that the average size of a web page is 20 kilobytes. Now, these are representative numbers from real life. Now, if you take 10 billion web pages, each of 20 kilobytes, you have a total data set size of 200 terabytes. Now, when you have 200 terabytes, let's assume that we're using the classical computational model, classical data mining model, and all this data is stored on a single disk, and we have to read it in to be processed inside a CPU. Now, the fundamental limitation here is the bandwidth, the data bandwidth between the disk and the CPU. The data has to be read from the disk into the CPU, and the disk read bandwidth for most modern SATA disks, a representative number, is around 50 megabytes a second. So we can read data at 50 megabytes a second. How long does it take to read 200 terabytes at 50 megabytes a second? You can do some simple math, and the answer is 4 million seconds, which is more than 46 days. Remember, this is an awfully long time, and this is just the time to read the data into memory. To do something useful with the data, it's going to take even longer. Right? So clearly, this is unacceptable. You can't take 46 days just to read the data, so you need a better solution. Now, the obvious thing that you think of is that if you can split the data into chunks, and you can have multiple disks and CPUs, you stripe the data across multiple disks, and you can read it in and process it in parallel in multiple CPUs. That's going to cut down this time by a lot. For example, if you had 1,000 disks and CPUs, instead of 4 million seconds, and we work completely in parallel, instead of 4 million seconds, we could do the job in 4 million by 1,000, which is 4,000 seconds. And that's just about an hour, which is a very acceptable time, right? So this is the fundamental idea behind the idea of cluster computing, right? And this is the standard architecture that has emerged for cluster computing is something like this. You have racks consisting of commodity Linux nodes. You go with commodity Linux nodes because they are very cheap. And you can buy thousands and thousands of them and rack them up. You have many of these racks. Each rack has 16 to 64 of these commodity Linux nodes, and these nodes are connected by a switch. And the switch in a rack is typically a gigabit switch. So there's 1 gigabit per second bandwidth between any pair of nodes in a rack. Of course, 16 to 64 nodes is not sufficient, so you have multiple racks, and all the racks themselves are connected by backbone switches. And the backbone switch is a higher bandwidth switch. It can do 2 to 10 gigabits between racks. Right, so you have 16 to 64 nodes in a rack, and then you rack up multiple racks, and you get a data center. So this is the standard cluster architecture that has emerged over the last few years for storing and mining really large data sets. Now, once you have this kind of cluster, that doesn't solve the problem completely, because cluster computing comes with its own challenges. But before we get there, let's get us idea of the scale, right? In 2011, somebody estimated that Google had 1 million machines, million nodes like this in stacked up. It's somewhat like this. So that gives you a sense of the scale of modern data centers and clusters, right? So here's a picture. This is what it looks like inside a data center. What you see there is the backup racks, and you can see the connections between the racks. Now, once you have such a big cluster, you actually have to do computations on the cluster, right? And cluster computing comes with its own challenges. The first and most major challenge is that nodes can fail, right? Now, a single node doesn't fail that often, right? If you just run a Linux node and let it stay up, it can probably stay up for 3 years without failing. 3 years is about 1,000 days. So that's, once in 1,000 days failure isn't such a big deal. But now imagine that you have 1,000 servers in a cluster. And if you assume that these servers fail independent of each other, you're going to get approximately 1 failure a day, which still isn't such a big deal. You can probably deal with it. But now imagine something on the scale of Google, which has 1 million servers in its cluster. So if you have 1 million servers, you're going to get 1,000 failures per day. Now, 1,000 failures per day is a lot. And you need some kind of infrastructure to deal with that kind of failure rate. Failures on that scale introduce 2 kinds of problems. The first problem is that if nodes are going to fail and you're going to store your data on these nodes, how do you keep the data and store it persistently? What does this mean? Persistence means that once you store the data, you're guaranteed that you can read it again. But if the node on which you stored the data fails, then you can't read the data. You might even lose the data. So how do you keep the data stored persistently if these nodes can fail? Now, the second problem is one of availability. So let's say you're running one of these computations, and this computation is analyzing massive amounts of data, and it's chugging through the computation, and it's run halfway through the computation, and at this critical point, a couple of nodes fail, right? And that node had data that's necessary for the computation. Now, how do you deal with this problem? In the worst case, you may have to go back and restart the computation all over again. But if you restart it now and the computation runs again, a node may fail again when the computation is running. So you kind of need an infrastructure that can hide these kinds of node failures and let the computation go to completion even if nodes fail. The second challenge of cluster computing is that the network itself can become a bottleneck. Now remember, there is this 1 gigabit per second network bandwidth that's available between individual nodes in a rack, and a smaller bandwidth that's available between individual racks. If you have 10 terabytes of data and you have to move it across 1 gigabit per second network connection, that takes approximately a day. You can do the math and figure that out. A complex computation might need to move a lot of data, and that can slow the computation down. So you need a framework that doesn't move data around so much while it's doing computation. The third problem is that distributed programming can be really, really hard. Even sophisticated programmers find it hard to write distributed programs correctly and avoid race conditions and various kinds of complications. So you need a simple problem that hides most of the complexity of distributed programming and makes it easy to write algorithms that can mine very massive data sets. So we looked at 3 problems that we face when we're dealing with cluster computing, and MapReduce addresses all 3 of these challenges. Right? First of all, the first problem that we saw was one of persistence and availability if nodes can fail. The MapReduce model addresses this problem by storing data redundantly on multiple nodes. The same data is stored on multiple nodes so that even if you lose one of those nodes, the data is still available on another node. The second problem that we saw was one of network bottlenecks. And this happens when you move around data a lot. What the MapReduce model does is that it moves the computation close to the data and avoids copying data around the network. And this minimizes the network bottleneck problem. And thirdly, the MapReduce model also provides a very simple programming model that hides the complexity of all the underlying magic. So let's look at each of these pieces in turn. The first piece is the redundant storage infrastructure. Now, redundant storage is provided by what's called a distributed file system. A distributed file system is a file system that stores data across a cluster, but stores each piece of data multiple times. So the distributed file system provides a global file namespace. It provides redundancy and availability. There are multiple implementations of distributed file systems. Google's GFS is, or Google File System, or GFS, is one example. Hadoop's HDFS is another example. And these are the two most popular distributed file systems out there. A typical usage pattern that these distributed file systems are optimized for is huge files that are in the hundreds of gigabytes to terabytes. But even though the files are really huge, the data is very rarely updated in place. Right? Once data is written, it's read very often. But when it's updated through appends. It's never updated in place. For example, let imagine the Google scenario once again. When Google encounters a new web page, it adds a web page to its repository. It doesn't ever go and update the content of a web page that it already has crawled. Right? So a typical usage pattern consists of writing the data once, reading it multiple times, and appending to it occasionally. Let's go under the hood of a distributed file system and see how it actually works. Data is kept in chunks that are spread across machines. So if you take any file, the file is divided into chunks, and these chunks are spread across multiple machines. So the machines themselves are called chunk servers in this context. So here's an example. There are multiple chunk servers. There's chunk server 1, 2, 3, and 4. Here's a file 1, and file 1 is divided into 6 chunks in this case: C0, C1, C2, C3, C4, and C5. And these chunks, as you can see, four of the chunks happen to be on chunk server 1, one of them is on chunk server 2, and one of them is on chunk server 3. Now, this is not sufficient. You actually have to store multiple copies of each of these chunks. And so we replicate these chunks. So here's a copy of C1 on chunk server 2, a copy of C2 in chunk server 3, and so on. So each chunk in this case is replicated twice. If you notice carefully, you'll see that the replicas of a chunk are never on the same chunk server. They're always on different chunk servers. So C1 has one replica on chunk server 1 and one on chunk server 2. C0 has one on chunk server 1 and one on chunk server n, and so on. Here's another file, D. D has 2 chunks, D0 and D1, and that's replicated twice. So that's stored on different chunk servers as well. Okay. Now, so we've sort of chunked files and stored them on these chunk servers. Now it turns out that the chunk servers also act as compute servers. And whenever computation has to access data, that computation is actually scheduled on the chunk server that actually contains the data. This way, you avoid moving data to where the computation needs to run, but instead you move the computation to where the data is. And that's how you avoid unnecessary data movement in the system. This will become clear when we look at some examples. So to summarize, each file is split into contiguous chunks. And the chunks are typically 16 to 64 megabytes in size. And each chunk is replicated. In our example, we saw each chunk replicated twice, but it could be 2x or 3x replication. 3x is the most common. We saw that the chunks were actually kept on different chunk servers. But when you replicate 3x, the system usually makes an effort to keep at least one replica in an entirely different rack, if possible. And why do we do that? We do that because it's the most common scenario is that a single node can fail. But it's also possible that the switch on a rack can fail. And when the switch on a rack fails, the entire rack becomes inaccessible. And then if you have all the chunks for all the replicas of a chunk in one rack, then that whole chunk can become inaccessible. So if you keep replicas of a chunk on different racks, then even if a switch fails, then you can still access that chunk, right? So the system tries to make sure that the replicas of a chunk are actually kept on different racks. The second component of a distributed file system is a master node. Now, the master node is also known as it's called the master node in the Google file system. It's called the name node in Hadoop's HDFS. The master node stores metadata about where the files are stored. And for example, it might, it'll know that file 1 is divided into 6 chunks, and here are the locations of each of the 6 chunks, and here are the locations of the replicas. And the master node itself may be replicated. Because otherwise it might become a single point of failure. The final component of the distributed file system is a client library. Now, when a client or an algorithm that needs to access the data tries to access a file, it goes through the client library. The client library talks to the master and finds the chunk servers that actually store the chunks. Once that's done, the client is directly connected to the chunk servers, and it can access the data without going through the master nodes. So the data access actually happens in a peer-to-peer fashion without going through the master node.